that's the only thing you will like. So thanks for staying so long. I don't know. This is. I'll show you the. Does it work? Yeah. So what is this talk about and what it's not about? So I kind of didn't even plan to give a serious talk here. I thought this will be more like a working meeting here. And when I learned that I'm supposed to give a talk, I have given like 5 propaganda talks this year alone, and last year in Paris around this time, I gave this long talk at Henri. So if you want to see a well-organized propaganda talk, just click on that and don't listen to me now. And I would also say that I will not speak about formalization because Adrian already talked about what we are now doing with Atle, which is quite a nice project which I like. And I think on the next slide there is a pointer to a history of auto-formalization talk that I gave last year at the trimester in Bonn. And I must say, I find myself in some weird phase transition from being a big propaganda guy about combining machine learning and theorem proving to being kind of a contrarian, saying that maybe you guys are trusting some of these hypes too much, and maybe you should be doing more rigorous science rather than some startup pitches. So you will probably be able to see where I am from these few remarks. One thing is that like the history of my propaganda talks goes way back, and one of the serious ones was actually done here at Institut Henri Poincaré, when homotopy type theory was all the rage and nobody knew anything about machine learning. So if you want to have some historical comparison with 11 years ago, you can click on these slides. And like there are other pointers here. Just for the fun, like these are the AITP challenges and bets that I declared at IHP in 2014 in this propaganda talk. So at that time we just had the kind of fresh results with Cezary Kališík mostly, that we could prove like 40% of the fly spec and Mizar top-level lemmas automatically by combining theorem provers with machine learning in various ways. So my bet, like these are actually bets for real money, for 10,000 euros, was that in 20 years, with the same resources, that's the big caveat which nobody seems to understand these days, we will be able to prove twice as many, 80%, and in 10 years, 60%. So we actually did that in like 2021. And there is the last one is this kind of auto-formalization bet. So this is just when we started to develop the first learning-based systems for auto-formalization. That 25 years from 2014, 50% of the top-level statements in LaTeX written master-level math curriculum textbooks will be parsed automatically and with correct formal semantics. And I think that there is kind of enough push for auto-formalization, especially with language models, that this may really go faster than I expected. But, well, whatever. So my history is that back in like almost 30 years ago, I was looking at how can people automate math, because it was somehow implicitly understood at the time that mathematics is the language of science. And we have this kind of embedding of mathematics into logic, and in principle we could we could thus transform all our problems to logic and solve them by theorem proving, right? So this was like some of the early AI ideas. And like I was looking at what these automated theorem proving people are doing, and I wasn't totally excited about the way they were doing it because of the combinatorial explosion they were immediately getting when working with large theories. So basically, I tried in my master thesis to get some reasonably big corpus of human like mathematics that I could feed to some theorem proving system and learn the heuristics that the humans are following. And this was the plan, and it mostly kind of stayed the plan. Like it was a very daunting task to do for all sorts of reasons. But like this was basically the master plan I declared 20 years ago. And I wonder how it's today related to your project, right? Like to Malinka. Because like, for example, at that time, the kind of learning approach could be seen as an alternative to this flagship AI project of Ducklenat in the US, which was like, let's just write the heuristic down manually, right? Like all the heuristics for problem solving, well, okay, maybe if you have a lot of funding, you will get a lot of people to write down a lot of problem solving heuristics. But then how do you combine them, right? Like so it felt to me that somehow all sorts of learning need to be involved in various ways. And it seems to me that today, like obviously with the ascent of the statistical machine learning, it's kind of believed by more and more people that maybe too much that we will learn this all just from the data. So that's kind of an introduction, and then now there will be a series of various random remarks. So one thing that also relates quite a bit to the history of ATP. Actually, what triggered me was Adrian's talk when he said that ATPs are today amazingly good in geometry, for example. So I actually did 10 years ago, I ran the state-of-the-art automated theorem provers on Tarskian geometry on the problems that Michael Beeson and Larry Wash were creating according to this Shmielev-Tarski book. And the state-of-the-art theorem provers couldn't solve it all, and neither could Beeson and Wallace. They introduced a guiding method that was kind of a cheating method that kind of allowed them to get Otter to kind of formally do the proof, but it was kind of a human guided proof. But like the way Adrian mentioned it actually leads to interesting history of automated deduction. So this is taken from Martin Davis' paper, Early History of Automated Deduction, where he very nicely distinguishes between these two camps or two paths which really formed in automated theorem proving. And one is kind of the logicians, the logicists, the people who come up with different calculi, and typically with some better and better calculi, better and better, you could say, symmetry breaking rules, like ways how to prevent the calculi to be super redundant and to be more efficient. And he doesn't explicitly speak about machine learning. This probably wasn't the idea at the time. But like what he speaks about in the second camp are the kind of heuristic people, right? Like, let's do it like humans, like Simon and Newell. Like, let's try to, like this duck-Lennart approach also, let's try to write down the problem solving heuristics. And what is funny, like again, you can think about it in today's context with these LLMs eating everything which is available out there, that in this paper, this was written, I think, for the handbook in 2000, he says the difficulty with the first approach was that available information about how creative mathematicians go about their business was and remains vague and anecdotal. So is this better today? Like I think Tim Gowers had this idea to write the, how do they call that, informed proofs, or something like proofs annotated with actually how the mathematician makes various decisions. But you could also say that this is today kind of learnable, right? Like that today we have so much material out there, both in the informal and maybe more and more in the formal world, that if you kind of jump on the machine learning bandwagon, this sentence of Martin Davis isn't anymore such a big deal, right? So it's kind of interesting to think about it in this. The kind of thing that triggered me when I heard Adrian to mention this geometry is that actually geometry, according to Martin Davis in this early deduction history, is the thing that led Robinson to basically start thinking about Herbrand universe as the important thing in automated theorem proving. And there is like a very direct analogy that he came up between like the geometry solvers and the generalized theorem proving, like the geometry, the way Galanter did his geometry machine or whatever it was, is kind of a special case of what you do when you are basically solving arbitrary logical problems, and we have a name for it, which is this Herbrand universe, and that's what these ATP people have been doing for decades now. So it's like an example of something which is very humanly accessible and maybe natural even. On one hand, like geometry, right? Like we have all these geometrical intuitions and stuff. And something which suddenly becomes like very logical and abstract. And like if you start speaking about Herbrand universe in a room full of machine learning people, they will switch off immediately, right? Like this is not what the LLM people are doing. I would say this distinction that Davis did is, to me at least, extremely relevant still today. So for example, the talk that Asea gave was basically about these orderings, which are an extremely powerful symmetry breaking methods in today's automated theorem provers like Vampire. And similarly in subsolvers, you have so advanced symmetry breaking methods, and you have even something that they call closed learning, right? And it's really very interesting to think about how to combine all these like very smart human engineered ideas, methods, calculi with various kinds of machine learning. And I should give credit to the Munich group like Stefan Schulz and Jörg Denzinger and others who really thought about it a lot already 1990s. So I just, because I started to talk about Martin Davis, I will randomly jump to speaking about this particular thing that we did quite recently, mostly with Jelle Piepenbrock. So it's like, if you put yourself into the fully machine learning believer camp, what you could do today to solve basically all these very hard problems, which are, I don't know, in TP, Isabel, Sledgehammer, Mizar, whatever, is take a first-order problem in any of these data sets and benchmarks. And if you have infinitely precise guessing power, just create the precise ground instances of these first-order clauses and give it to a SAT solver. The SAT solver is not the issue. The SAT solver is superhuman, super powerful, and has been superhuman and super powerful for like two decades at least. So the kind of question is the machine learning so powerful, right? So we tried to test this particular. It's like Martin Davis today, right? Like Martin Davis after 60 years or so. Can we come up with reasonable machine learning architecture that we will train it on some proofs and how the first order clauses get instantiated there to get the propositional problem that is then easily solved by the SAT solver, and then can the trained architecture propose instantiations for like new problems that we throw at it. So like if you're interested, read this paper. The upshot is kind of yes, but kind of not so much yet, at least. Like we are definitely not better than the standard instantiation based theorem provers and their heuristics in this particular way, which is like very ambitious. Like you look at the first order clause with quantifiers and you ask some chat GPT or whatever, maybe just GPT, now please produce the ground terms that you should plug into this clause for these variables. So what yielded is an architecture which is different from what most the language modeling people are doing today, in the sense that it's signature symbol independent. And that's for a good reason, because in these problems there are typically many auto-generated column symbols. And the way these symbols are auto-generated is inconsistent between different problems. So if you started to trust the names in the way how the transformer architecture kind of trusts the names, you would get very inconsistent data to train on. And actually, if we do like kind of a reasonably fair comparison between the transformer and this anonymous GNN to RNN architecture, then the anonymous architecture beats the transformer. I should say that we haven't tried like these newer heavy chain of thought reasoning models on this. But then again, it's a question of the resources, right? Like once you start using the heavy chain of thought models, you somehow need to compare it with the resources that you invest into like this architecture that yielded it. One other remark which kind of plugs back to this logicist versus the heuristic or learning people is that this particular approach that we started to do was very, very significantly improved when we, instead of just calling a SAT solver, which means that you have to instantiate also all the clauses that encode equality. Typically in these instantiation-based theorem provers, you really do it in a way where you have axioms for symmetry, transitivity, reflexivity, and congruence of equality, and that's fine. Like you can do it that way. You can try to instantiate these clauses, But typically, to solve these problems, you really need to instantiate many of these clauses because equality is like very prominent in a lot of these problems. And if you, instead of that, go with a slightly smarter approach, which in this case means just calling the kind of well-known decision procedure for ground clauses with equality, then suddenly your task is much, much easier because you are now supposed to guess maybe only half or maybe even less of the instantiations of the first order clauses. So this was really like a big performance boost that we did just by being smarter on the logic side, like trivially smarter, and not kind of relying so much on the machine learning side, because the machine learning side really wasn't super smart. As I said, it would be interesting to try it with the more heavy-duty reasoning models today. Like the way we kind of do these things today are these kind of learning, proving feedback loops, like this particular experiment. And that's like one thing that like I said initially back in 1996, my thinking was, well, let's just try to learn from the human math textbooks, etc. And like I guess somewhere in the back of my mind there was the idea that we will kind of combine it with the reasoning and deduction, etc. A bit like I guess this guy is talking about in his book called Science and Method. And I guess I was really surprised when I really started to do it. So I did the first system which really does this feedback loop between proving and learning like 10 years later in 2006, this machine learner for automated reasoning, Malaria. And like it was surprising how much it can really, how far it can really go in this kind of self-learning feedback loop between the proving and learning. The one issue with it, which again may be relevant today for kind of the LLM camp, which tries to, in the extreme case, get rid fully of the formal proof, is that I really had to debug my translation of the Missile library to first order theorem provers a lot, because like the machine learning technology is very lazy, greedy. Like this is a well-known fact repeated over and over in the history of AI. If you have some very simple patterns that your learning method can learn from, they will kind of hang on or catch on those patterns rather than being forced to do the hard stuff. So for example, when I had still like a slightly inconsistent translation of Missile to first order logic, these self-learning feedback loops would kind of devolve because they would catch on the inconsistencies. The very small number of inconsistencies which I had there would become very prominent once you start working with a greedy, lazy machine learning system. So I kind of debugged it for Missile, and like Larry Paulson got interested back in 2007 and sent me his Isabel problems. And he had like, I think 3 different translations at the time. And one of them was unsound, and that was the most efficient for the normal automated theorem provers like Vampire, eProver, Spass, etc. And so he naively sent me those problems because he was interested in the performance improvement. And like this beast has solved all his quote-unquote hard problems in like 10, 20 minutes by finding the easiest unsoundness that he had there, which happened to be present in all the problems, and then trivially solving on his all of his problems, because once it knows how to exploit it will always go after that. And the interesting thing is that with the non-learning systems, you don't get that. Like his translation was still very useful to the standard automated theorem provers who didn't have this learning capacity, because it was kind of unnatural for them to exploit the unsoundness there. So I'm saying this like for the last, let's say, 20 years, I have been doing a lot of these feedback loops, and always beating my collaborators and students, telling them, like, you really need to make it right, otherwise the system will devolve, like in these cases, which I heard hard about in the beginnings. But it seems to me today that the LLM people are kind of going in that direction. Like if you look at this DeepMind OpenAI latest breakthroughs in solving IMO just with the language model, apparently, like obviously nobody knows anything about it, so maybe it's just apparently that there is no formal proof checking. So I don't know, like maybe the language models can really be pushed to be so critical of the supposed proof that they will reject it and that they will kind of behave as a proof checker. But I don't know how far this can be pushed. I'm kind of really interested in whether this will scale to kind of new math, etc. Yeah, so as I said, like these feedback loops are for me one of the most interesting things that we are today doing, and I think they can be done both in the kind of human-friendly math settings and also in like these very human unfriendly settings. So one thing I did quite early, because it was very productive, was, for example, a similar feedback loop for evolving strategies for automated theorem provers, where you are evolving something which is kind of symbolic and which is kind of guiding the automated theorem prover, but it's a program for the automated theorem prover. It's not something very human-friendly. What may be kind of more human-friendly was when we really started to seriously look at internal guidance of automated theorem provers. So, for example, in Tableau provers, specifically in connection Tableau, the calculus is kind of human-friendly. You kind of always operate on something relatively small, like this partial connected Tableau. And you kind of feed it to your machine learner, whatever it is, some graph neural network. And the graph neural network is supposed to do this kind of Monte Carlo tree search, like in the AlphaGo, AlphaZero systems, and maybe grow some human-friendly intuitions, like should I play this move or should I play this move? Is this Tableau close to completion, or is this Tableau something that will not succeed for a long time? So that may be one example of a relatively human-friendly proof setting that can be guided by machine learning. Then there is the internal guidance of the state-of-the-art automated theorem provers, like these saturation provers, like Vampire and eProver, like in these Enigma and DeepIR systems, where again it's kind of very I don't know whether we can call these things to be very human-friendly proof, but yeah, they are really the state of the art today. And then obviously there's this whole business of guiding tactical provers, which probably started with this tactic-toe system by Thibaut Gauthier, which is really seems to be today like the preferred direction for the deep learning community, because it's sufficiently high level. it works, it fits reasonably like the language modeling situation because you can do all sorts of stuff. So that may be like the kind of most human related proving. And I already mentioned like these instantiation provers. So what I showed you before was like this very ambitious setting where we really synthesize the ground instances of the first order clauses. You could do the same for high order clauses if you are super ambitious. But like what you can also do is to guide the instantiation processes of the instantiation-based provers like iProver and CVC5. So that actually works better. And that's also interesting. Like it's somehow shows that, so for example, what we did recently when we got like a 20% improvement in CVC5 over the MESAR dataset, we really just guide we tell CVC5 which of the clauses in its current proof search it should try to instantiate, but we don't tell it how it should instantiate them. We kind of leave it up to CVC5's smartness to use all of its carefully invented methods to decide how to instantiate. And we just give it kind of this very high level instruction, now instantiate this particular clause. So again, like it shows you the kind of what works, right? Like here we can improve state-of-the-art SMT solver by 20% if we do it in a reasonable, not super ambitious way. Whereas we cannot really improve it if we do it in the very ambitious way when we try to generate the ground instances ourselves. So I just wanted to show you one example of this proving learning feedback loop. Like this is kind of canonical for me, like we did it in 2019 by putting some kind of machine learning guidance into eProver. So that's this Enigma system. And the way it works is that you start with some 15,000 proofs that eProver can solve without any guidance in 10 seconds. Then you train, in this case, some gradient-boosted decision trees, which are reasonably fast and efficient. You plug them back into the eProver. And once you have them there, they help you guide eProver in a smarter way. And then you solve more problems in the kind of second iteration, and then you train it again, and then you solve more problems, etc. So if you do this about 6 times, it gives you 70% improvement. And the very, very important thing here is that we don't cheat. So this is all done on a single CPU in 10-second CPU time. So this is really apples to apples comparison with the other methods that people develop in automated theorem proving. Like if you push it further, we eventually got to the 75% in 2021. And this is kind of the kind of victorious email that I wrote when we when we reached the 75%. So again, like just as a comment to the thing that started, let's say, in 2022 with the LLM people, like you can do like very, very strong things without LLMs, right? Like this is before LLMs. And like there is more of it. So there is like, for example, this DPIR architecture, which goes even more radical than, for example, this Enigma guidance. I will not go into the details in how little information it collects for the machine learning and how efficiently it uses it for the guidance of the theorem prover. I'll probably skip. I should say another thing which people, for their own shame, do not know much about is the amazing work done by Bob Veroff and Michael Quignon and J.D. Phillips and this community over open problems in equational algebra. And these are really proofs of open conjectures in, let's say, quasi-group and loop theory, which reach like 200,000 inferences. Like Bob Veroff really has proofs that are crazy, crazy long. And what he called it is the hints method or hints guidance. And what I call it is symbolic machine learning. So he doesn't like me saying that he does machine learning, but I think it's appropriate. So what he does is like a clever human-guided theory exploration when he creates many related problems. So some of them are easier, some of them become harder and harder. And as he solves the easier problems, he extracts hints from the proofs. And these are basically just the lemmas in the proofs. And then he used these lemmas as some kind of islands of safety when he goes from the axioms to the conjecture in the kind of harder theory, harder problem. He knows that when he arrived at some of these lemmas that were useful in the easier problem, for example, when the theory had some additional axiom in it, he knows that he can kind of assume that this is a good thing and that he can focus on inferencing with this lemma that he now achieved. So it's obviously not 100%. There is a lot of interesting technology in it. But it's really like an amazing symbolic, I call it symbolic learning guidance for today's automated theorem provers, which really lead today's automated theorem provers to solve open conjectures. And it's a shame that people don't know about it. It's really one of the biggest achievements of automated theorem proving. I also wanted to mention, like, very recent, this year at CADE, work on Vampire by Martin Suda. So he basically, by doing this like very efficient symbol-independent machine learning, which slows down Vampire only by 30%. Like this runs on a CPU. Again, this is all very precise, rigorous comparison of the unguided Vampire with respect to the number of CPU instructions. So he slows it down only by 30% by having like very nicely integrated efficient neural networks into Vampire. And he made 20% improvement on the test set on TPTP after he improved it by different methods, by the strategy evolution methods, by 27% in CASC last year. So like, again, like you don't read these things in the quanta, nature, whatever, but these are really amazing improvements that are happening. Yeah. So by the way, he solved several problems in TPTP where people even didn't know what their status is supposed to be, whether they are supposed to be provable or counter-satisfiable. And he proved quite a few problems where people assume that they know the status, but no automated theorem prover was able to prove them. Yeah, and it would be interesting, take one of these IMO-trained LLMs and try that, right? Or one of these DeepSeeks, like these reasoning LLMs today, and try to see whether you can do the same, and with what resources. So this is the architecture, just to show you a bit of the details. So he has, like, in the very beginning, he throws the initial clauses in the problem to this symbol independent graph neural network. And it gives him initial embeddings for the symbols and for the clauses. And then he has two like very fast, tightly integrated recursive neural networks. One he calls generalized weight and one he calls generalized H, because this is some automated theorem proving tradition, which like basically each time you create a new term, you apply some like very quick neural layer, basically just once, because you already have the embeddings of the argument symbols, and you basically just apply the one step of the recursive neural network, which kind of takes these arguments and makes the embedding of the new term, which with its head operator. So this is like a operation that is done each time a new term is created, and which is done like very efficiently in this way. Like it's basically integrated with the term data structures in Vampire. And the generalized weight works similarly for clauses. So it's some kind of like very fast neural network that ranks the clauses. Yeah, so this was about like these low-level ATP guided things. I wanted to also, again in this Malinka natural language, etc. Context, discuss like this kind of dream with which I kind of was infected some 30 years ago, and like this LLM dream that emerged, I would say, in the minds of many people when ChatGPT got released and they discovered machine learning. And I'm still kind of thinking how these two worlds connect and interact and work together. So you probably all know here the QED manifesto, like it was this project to build like the formal encyclopedia of all math knowledge and techniques. And they have these quotes by Gödel that, I don't know, math will basically reduce to logic. And then by Whitehead that math understanding will be all of the understanding, right? So if you take him seriously, you would say we will move from Reddit discussions or Twitter discussions to mathematical discussions, right? Like I don't know whether we are succeeding in that. And then there is, like this is also in the QED manifesto, this is the quote by the Brown. Again, like about like this this idea of creating like this crazy formal encyclopedia of all mathematical knowledge, and as somebody pointed out, it kind of goes back to Peano. They do have some comments about AI, but they are kind of mostly negative in the QED manifesto. So they are saying that like you can but don't have to build this database of math with AI, whatever they meant by AI at the time. Maybe they even meant automated theorem proving as AI at the time. And I think the interesting point is that they insisted on this kind of formal proof checking aspect there. Like they are kind of agnostic, but saying whatever it is it produced by a machine, by a heuristic, by a human, it should be checkable, and that will be this kind of consistency layer that we will have. And yeah, again, like we kind of don't have it today for kind of the LLM dream, right? Like for this one big internet eaten by the LLMs today. And the other kind of remark which I wanted to speak about a bit is like what are the analogies and differences between how, for example, especially this reasoning LLMs that emerged relatively recently have compared to the automated theorem provers? So I was actually asked by a journalist recently. So I think you probably all know some of these things, but maybe not completely. So I would say, like, if you think about what a language model is, if it's totally untrained, it's a token prediction generated model, and it will just generate strings, right? And the way how I explained to the journalist what an ATP is, because everybody now knows about what kind of LLMs are, is that it's kind of an LLM, but it's constrained by logic, right? Like it can also produce a huge amount of junky clauses, etc. But like we know that those junky clauses at least follow from the previous clauses, and in the kind of untrained situations, this is the only difference, right? Like the LLM is producing arbitrary strings, the ATP is producing arbitrary clauses. Now, like we can obviously put some statistical guidance, like in the case of neural language models, we put a neural network there. In the case of automated theorem provers, again, like we can put, for example, a graph neural network, etc. So one way how to understand the kind of modern ATPs with a maybe big grain of salt as basically logic constrained LLMs, right? Like you could kind of do it like that and then start quarreling with the LLM people. Yeah, well, then there is the training. One funny thing is how all these concepts emerge in the deep learning community. So what we have been calling premise selection since like 2003, when reasoning over these large knowledge bases like Mizar, Isabelle, FlySpec, etc. The LLM people started to call retrieval augmented generation at around 2020. And the idea, it's again like one interesting analogy there. If you give to the automated theorem prover the whole Mizar or Isabelle library, its chance of getting the proof is really, really low. Like if you aren't reasonably smart in the kind of selection of the knowledge, the performance devolves a lot. Apparently, this also works for the LLM. So if you give it the right facts to focus on, then its kind of inference, whatever that means, also goes up quite a bit. So it's kind of interesting to think about, like initially, like the way the kind of LLM maximalists were talking about it. Well, we will just eat it all and it will do the right thing, but apparently not, right? Like apparently the prompting with the right relevant knowledge helps a lot. The similar thing are these feedback loops. Like you didn't see it so much before DeepSeek, but I think with the DeepSeek publication, it really became out in the open, that you can train the LLMs in this kind of reinforcement learning loop, where you have some solution of the mathematical problem in the end, for example, some number which is kind of unlikely to reach, and you maybe have some kind of curriculum of problems like easier and harder, and somehow the kind of LLM gets there by having basically all of the world's knowledge and learning how to use this world's knowledge for a proof search. Like you could call it something like proof search. So I think one one question, and maybe a research problem for the Malinka community, which occurred to me, is like, maybe at some point, like if we have like these self-learning loops for these very big beasts, could it be that the LLM will convince itself, like learn from these reinforcement learning feedbacks, that it's actually good for it to follow the rules of logic? Like, could it be that it discovers on its own that whatever it's doing when it's trying to solve these mathematical problems by this kind of tree of thought reasoning, it will actually like emerge from that, like the kind of rules of formal proof. So for me, this sounds like an interesting research problem. I don't know how much time I have. Should I start? 5 minutes. Okay. So because this is about natural language, I was just in Poland at the Polish Logic Congress, and I was in a university where this guy, Stanislav Jaškovský, apparently was a rector at some point. So this is what the Mizar people did in 1970s was actually take not the Gensen stuff, which actually came later, but the Jaškovský stuff, this paper that he published in 1934 that is called On the Rules of Suppositions, where he basically defines what the Mizar people then started to call the declarative proof style. So there is some history to it. I think the first person who brought it to the West was John Harrison, who interacted with the Mizar guys at the second QED workshop in Warsaw, and then obviously Makarius, Naproš, the sub people, etc. And like one question that I always had for the linguists, which are somehow present in Malinka, which occurred to me like back in 2011 when I employed an Naproš guy, was is there a direct or indirect link between the Jaškovský style natural deduction and what the linguists call discourse representation theory? So the way I started to think about it was that at some point 20 years ago I re-implemented the Mizar data structures that do this. And then, I don't know, 6 years, 7 years after that, I saw a talk about Naproš given by Daniel Kulwein, where he called basically the same data structures in Naproš. He called them discourse representation theory. So there is some link here, which maybe somebody could explore, but maybe it's trivial and everybody knows that. What is interesting probably for the Malinka project are whether the declarative proofs are somehow superior for ATPs, for proof search, for automated proof. And I would say even in the ITP setting, and I pointed it out during Makarius' talk, it's not fully clear that the declarative proofs are always preferable. I think the community is quite a bit still on the tactical side rather than on the declarative side. And I hear from various people that, for example, for the software and hardware verification, the tactical proofs are preferable to the kind of declarative proof style. One interesting point made this year at AITP by Mantas Bakshis from the Kimina team was that they are not better for this reinforcement learning loop they do over Lean for IMO, but they are easier to debug for the humans, easier for the human developers. And I don't know, like if you want to go in the direction, like 5 years ago, I did this GPT-2 experiments over the Mizar declarative proofs. My impression at the time was that GPT was still very bad in understanding the semantics of these declarative proofs, and it was producing. It was a bit similar to this Karpatis experiment with stacks in 2015, where you produce plausibly looking mathematical gibberish, but the semantics is very hard for the language model. But this was in 2020, obviously. It's unclear how strong the kind of much bigger models are today. Again, like I would perhaps argue that if you want to go in the direction, you may want to invest in some kind of better generalizing architectures like these anonymous graph neural networks, rather than at the kind of vanilla transformer architecture, which really relies on the names a lot, and if you rename things, it may stop working, etc. I would also say that the comment you would get from the classical logicist automated theorem proving people is that this is very distant from like all these symmetry breaking methods that the ATP people have shown to be so powerful. So that's another disadvantage of trying to do automated theorem proving by producing the declarative proofs. And on that note, I will just mention the very recent experiment we did with Theo and to some extent Jonas Bayer, which was motivated by Cyril Cohen's talk in Sweden. So we, and actually Makarius also mentioned the problem of reconstructing sledgehammer proofs in Isabel. So what we tried with Theo is that I gave him 10,000 hammer proofs for Mizar, done by Vampire or eProver. And he tried to fine-tune this Qwen 32 billion model to get them, to massage them into a nice, beautiful declarative Mizar proofs. And he actually gets some successes. I don't know if I have it somewhere. Yeah, I don't have the success rate. So I think it's like he got now 20 nice Mizar checkable declarative proofs out of these horrible TP-TP blobs by running this 32 billion Qwen model, which actually does a lot of reasoning. So I don't want you to read this, but like this is the output of the Qwen language model when it gets the horrible TP-TP proofs, and it kind of does its own reasoning to come up with a readable declarative proof. So that's maybe one way how to get from these like automated proofs to beautiful human-friendly proofs, fine-tune a large language model. So that's it. I don't know, like these 30 years ago, I really thought that it will be interesting to start learning theorem proving from humans. And I wonder if I still believe it, and maybe to some extent. I think the kind of interacting with all these tools taught me that the situation is quite a bit richer and more interesting, that the human math and human proofs aren't everything. Like I think the inhuman, the tool produced, the ATP produced, the AI produced proofs will be more and more prominent, and that's maybe exciting. And there may be like all these analogies with things like machines playing chess and Go. And if you want to hear about like the very interesting latest experiment which we are doing over OEIS, then come to KickOn next week in Brazil, I will say about it. Thank you.
So are there questions or comments for discussion? Okay.
Everybody's tired.
Yeah, I mean, we can carry on outside of the room and discuss offline. Yes, I think it's very reasonable. So, yes. So, I mean, I think Hugo, Carlos, Philippe, and all the people working, you know, at the Malinka team, we would like to thank you. I mean, all of you, and as we said at the very beginning, like 3 days ago, we see the project as a, you know, way to, I mean, build a community of people around, I mean, Europe, the world, working on these topics. It's really exciting. There are many elements, I think, yes, you know, I mean, we saw that these 3 days, many elements to combine together. At the same time, the feeling of convergence. So it's very open and fast evolving. So yeah, I'm sure we'll meet again soon in one way or the other. So thank you. Yeah.